Do you know how to launch a satellite in its orbit? Do you know how a satellite moves in a certain orbit? Do you know which type of satellite we use for radio and TV communication purposes or for distance communication?
Good morning, children. Welcome to today's lesson on motion of satellites. I hope you are well aware with the applications of modern technology, especially about the artificial satellites. An artificial satellite is a man-made object which has been placed into an orbit by human endeavor. Such objects are called artificial satellites so as to distinguish them from natural satellites, that is, the moon. Artificial satellites continuously orbit the Earth or some other celestial body in space. Most of the artificial satellites orbit the Earth. Such type of satellites are used for weather forecast, transfer telephone calls over the oceans, assist in the navigation of the ships and aircrafts, monitor crops and other resources, and support military activities. Artificial satellites are also useful to study the universe. Some artificial satellites have orbited the moon, the sun, and the planets Venus, Mars, Jupiter, and Saturn. Such satellites mainly gather information about the heavenly bodies they orbit. Today, we will study the basics of satellite motion without going into details of the technology. Before this discussion, let me share the learning objectives of today's topic with you.
Learning objectives. On completion of this topic, learners will be able to define Earth satellites and discuss the nature of their motion, derive the relation to calculate the time period of the Earth satellite, derive an expression to calculate kinetic energy of an orbiting satellite, derive an expression to calculate potential energy of an orbiting satellite, calculate the total mechanical energy of an orbiting satellite, discuss different types of artificial satellites and their importance.
The motion of a satellite is a direct consequence of the Earth's gravity. Once launched in the appropriate orbit, these man-made crafts orbit around the Earth without any propulsion. Their motion is very similar to the motion of planets around the Sun and hence obeys Kepler's laws of planetary motion. In particular, their orbits around the Earth are circular or elliptic. ਅਸੀਂ ਜਾਣਦੇ ਹਾਂ ਕਿ ਜਦੋਂ ਸੈਟੇਲਾਈਟ ਅਰਥ ਦੇ ਸਰਫੇਸ ਤੋਂ ਬਹੁਤ ਦੂਰ ਹੁੰਦਾ ਹੈ ਤਾਂ ਸੈਟੇਲਾਈਟ ਤੇ ਸਿਰਫ ਗੁਰੂਤਾ ਬਲ ਹੀ ਨਹੀਂ ਲੱਗਦਾ, ਖਾਸ ਕਰਕੇ ਜਦੋਂ ਸੈਟੇਲਾਈਟ ਧਰਤੀ ਦੀ ਸਤ੍ਹਾ ਤੋਂ ਬਹੁਤ ਉੱਚਾ ਹੋਵੇ। ਕਿਉਂਕਿ ਦੂਜੀ ਅਵਸਥਾ ਦੇ ਮੁਕਾਬਲੇ ਅਰਥ ਕਲੋਜ਼ੈਸਟ ਮੈਸਿਵ ਬੋਡੀ ਹੈ, ਜਿਸ ਕਰਕੇ ਅਰਥ ਦਾ ਗ੍ਰੈਵਿਟੇਸ਼ਨਲ ਅਟਰੈਕਸ਼ਨ ਹੋਰ ਬੋਡੀਜ਼ ਦੇ ਪ੍ਰਭਾਵ ਨੂੰ ਖਤਮ ਕਰ ਦਿੰਦਾ ਹੈ। Mass of an artificial satellite is negligible in comparison to that of the Earth. The center of mass of the two-body system is about same as the center of Earth. There are possibilities of different orbits, which are essentially elliptical with different eccentricities. A satellite close to the surface up to 2000 km moves nearly in a circular path. In this class, we will confine ourselves to the analysis of satellites having circular orbits only. ਧਰਤੀ ਦੇ ਦੁਆਲੇ ਮੂਵ ਕਰਨ ਲਈ ਸੈਟੇਲਾਈਟਸ ਦੀ ਇੱਕ ਸਪੈਸਿਫਿਕ orbital velocity ਹੁੰਦੀ ਹੈ। ਇਹ ਅਰਥ ਦੇ ਸੈਂਟਰ ਤੋਂ ਇਸ ਦੇ ਡਿਸਟੈਂਸ ਉੱਤੇ ਡਿਪੈਂਡ ਕਰਦੀ ਹੈ। ਸੈਟੇਲਾਈਟਸ ਨੂੰ ਅਰਥ ਦੇ ਸਰਫੇਸ ਤੋਂ ਰਾਕਟ ਦੀ ਸਹਾਇਤਾ ਨਾਲ ਲਾਂਚ ਕੀਤਾ ਜਾਂਦਾ ਹੈ, ਜੋ ਉਸ ਨੂੰ ਟੈਂਜੈਂਸ਼ੀਅਲ ਸਪੀਡ ਨਾਲ particular orbit ਤੇ ਸਥਿਰ ਕਰ ਦਿੰਦਾ ਹੈ। First of all, let me show you the principle of launching a satellite.
Suppose we have a several kilometers high tower on the surface of the earth. If a stone is thrown from the top of the tower with a horizontal velocity, it may hit the surface of the earth at point A after moving along a parabolic path. If the stone is thrown with a greater horizontal velocity, the stone will meet the earth at the point B, a little away from the foot of the tower. If the velocity of the projection is further increased in such a way that the stone falls freely under gravity, that is, it will be attempting to fall to the earth but missing all the time. The result will be that the stone will follow a circular path around the earth. As the stone is moving around the earth, it may be called an artificial satellite of the earth. However, an artificial satellite is launched into space with the help of at least two-stage rocket. The satellite is placed at the tip of the rocket. The first stage of the rocket takes the satellite vertically up against the gravity to the desired height of its orbit above the surface of the earth. Then the first stage of the rocket detaches and the second stage tilts it through 90 degrees. The second stage is used to impart required horizontal velocity to the rocket to make the satellite revolve in a circular orbit around the earth. This horizontal velocity is called critical orbital velocity, or simply orbital velocity, and depends on the height of the orbit. However, the magnitude of the horizontal velocity imparted to the satellite determines the successful launching of the satellite.
Satellite ਦੀ orbital velocity ਸੈਟੇਲਾਈਟ ਨੂੰ ਧਰਤੀ ਦੇ ਦੁਆਲੇ orbit ਵਿੱਚ ਸਥਿਰ ਕਰਨ ਲਈ required velocity ਹੈ। Let us determine the orbital velocity of a satellite.
Suppose that a satellite of mass m has to be put into circular orbit around the earth at height h above its surface. Consider that earth is a sphere of mass me and radius re. Then the radius of the orbit of the satellite will be re plus h. Suppose that v is the required orbital velocity for the satellite. Since a satellite is orbiting along a circular path, there is requirement of a centripetal force which is always directed towards the center of orbit. The gravitational force of attraction between the satellite and the earth provides the necessary centripetal force to the satellite to move around the earth in a circular orbit.
Hence, Fg is equal to mv square upon re plus h, or g into the product of me and m upon square of re plus h is equal to mv square upon re plus h. On solving this, we get v square is equal to g into me upon re plus h, or v equal to the square root of g into me upon re plus h. ਇੱਥੇ ਧਿਆਨ ਦੇਣ ਵਾਲੀ ਗੱਲ ਇਹ ਹੈ ਕਿ ਸੈਟੇਲਾਈਟ ਦੀ orbital velocity ਸੈਟੇਲਾਈਟ ਦੇ ਮਾਸ ਤੇ ਨਹੀਂ ਪਰ orbit ਦੇ radius re plus h ਅਤੇ planet ਦੇ ਮਾਸ me ਤੇ depend ਕਰਦੀ ਹੈ। ਕਿਉਂਕਿ g me ਦਾ ਗੁਣਨਫਲ ਜੋ ਪ੍ਰਾਪਤ ਹੋ ਰਿਹਾ ਹੈ constant ਹੈ। ਅਸੀਂ ਵੇਖ ਸਕਦੇ ਹਾਂ ਕਿ v ਧਰਤੀ ਤੋਂ ਸੈਟੇਲਾਈਟ ਦੀ ਦੂਰੀ ਦੇ square root ਤੇ inversely proportional ਹੈ। ਇਸ ਦਾ ਭਾਵ ਹੈ ਕਿ ਧਰਤੀ ਤੋਂ ਜ਼ਿਆਦਾ ਦੂਰੀ ਉੱਤੇ सैटेलाइट घट वेलोसिटी नाल मूव करता है. We can rewrite the equation of orbital velocity in terms of acceleration due to gravity. At the surface of the Earth, acceleration due to gravity, denoted by small g, is equal to g into me upon re square. That is, g into me is equal to small g into re square. On substituting the values of g into me, the expression for orbital velocity becomes v equal to square root of small g into re square upon re plus h, or v equal to re into square root of small g upon re plus h. For a satellite orbiting very close to the surface of Earth, h can be neglected in comparison to re. Then the expression for orbital velocity becomes v0 equal to square root of g into me upon re, or v0 equal to square root of small g into re. Do you observe any comparison between the escape velocity and the orbital velocity? Notice carefully. When the satellite is very close to the Earth's surface, its escape velocity is root 2 times the orbital velocity. Now, can you measure the orbital velocity of a satellite orbiting very close to the Earth's surface? By substituting the values of small g, which is equal to 9.81 meter per second square, and re, which is equal to 6.4 into 10 to the power 6 meter in the expression, the required orbital velocity comes out to about 7.92 kilometers per second.
It is to be noticed that the orbit of the satellite may not be circular in shape. As we move away from the Earth's surface, the orbital velocity also decreases.
This fact has a compounding effect on the time period of the satellite. A satellite at a greater distance has to travel a longer distance in one revolution than the satellite closer to the Earth's surface. At the same time, orbital velocity decreases as we move away. It is then necessary that time period of revolution increases for satellite at greater distances. Let us calculate the time period of a satellite in an orbit. Time period of rotation. ਧਰਤੀ ਦੇ ਦੁਆਲੇ ਸੈਟੇਲਾਈਟ ਦੇ ਇੱਕ ਚੱਕਰ ਨੂੰ ਪੂਰਾ ਕਰਨ ਲਈ ਲੱਗੇ ਸਮੇਂ ਨੂੰ ਸੈਟੇਲਾਈਟ ਦਾ ਟਾਈਮ ਪੀਰੀਅਡ ਆਫ ਰੋਟੇਸ਼ਨ ਕਹਿੰਦੇ ਹਨ. ਇਸ ਲਈ ਸੈਟੇਲਾਈਟ ਦਾ ਟਾਈਮ ਪੀਰੀਅਡ t बराबर है सर्कुलर पाथ का सर्कमफ्रेंस अपॉन ऑर्बिटल वेलोसिटी. m मास ਦੀ ਸੈਟੇਲਾਈਟ ਤੇ ਰੋਟੇਸ਼ਨ ਦਾ ਟਾਈਮ ਪੀਰੀਅਡ ਜੋ ਧਰਤੀ ਦੇ ਸਰਫੇਸ ਤੋਂ h ਹਾਈਟ ਤੇ ਰੋਟੇਟ ਕਰ ਰਿਹਾ ਹੈ ਇਕੁਅਲ ਹੋਵੇਗਾ 2 ਪਾਈ ਇਨਟੂ re plus h upon v ਦੇ. On substituting the value of orbital velocity v, that is square root of g into me upon re plus h into the expression of t, we get t equal to 2 pi into re plus h upon square root of g into me upon re plus h, which is equal to 2 pi into square root of cube of re plus h upon g me. A expression circular orbit which satellite ਤੇ revolve ਕਰਨ ਦਾ time period ਹੈ. Like orbital velocity, the time period is also independent of the mass of the satellite. Now, squaring both sides, we get t square equal to 4 pi square into cube of re plus h upon g me. Clearly, you can analyze that the square of time period of a satellite is proportional to the cube of the linear distance for the circular orbit. That is, t square is proportional to the cube of Re plus h, which is Kepler's law of periods as applied to the motion of satellites around the Earth. We can rewrite the equation of time period in terms of acceleration due to gravity. At the surface of the Earth, acceleration due to gravity, small g, is equal to g into me upon Re square. That is, g into me is equal to g into Re square. On substituting the value of g and me, the expression for time period becomes t equal to 2 pi into square root of cube of Re plus h upon g into Re square, or 2 pi upon Re into square root of Re plus h whole cube upon small g. ਧਰਤੀ ਦੇ ਸਰਫੇਸ ਦੇ ਨੇੜੇ orbit ਵਿੱਚ ਸੈਟੇਲਾਈਟ ਲਈ h ਨੂੰ Re ਦੇ ਮੁਕਾਬਲੇ ਨੈਗਲੈਕਟ ਕੀਤਾ ਜਾ ਸਕਦਾ ਹੈ। ਇਸ ਤਰ੍ਹਾਂ ਟਾਈਮ ਪੀਰੀਅਡ ਦਾ ਸਮੀਕਰਨ ਬਣਦਾ ਹੈ t0 equal to 2 pi into Re cube upon g me ਦਾ square root, ਜਾਂ t0 equal है 2 pi into Re upon small g the square root. Now, can you measure the time period of a satellite orbiting very close to the Earth's surface? By substituting the values of g, which is 9.81 meter per second square, and Re, which is equal to 6.4 into 10 to the power 6 meter in the expression, then the required time period comes out about 5072.4 seconds or 84.6 minutes. Knowing the time period of a satellite orbiting in an orbit, we can also measure the height of the satellite from the Earth's surface. From the expression we have t square equal to 4 pi square into cube of Re plus h upon g me. On rearranging, we get cube of Re plus h equal to g me into t square upon 4 pi square, or Re plus h is equal to cube root of g me into t square upon 4 pi square. Therefore, h is equal to cube root of g me into t square upon 4 pi square minus Re. Similarly, we can rewrite it in terms of acceleration due to gravity by substituting g me equal to small g Re square, and we get h is equal to cube root of g into Re square t square upon 4 pi square minus Re. ਜਦੋਂ ਕੋਈ ਸੈਟੇਲਾਈਟ orbit ਵਿੱਚ planet ਦੇ ਦੁਆਲੇ ਚੱਕਰ ਲਗਾਉਂਦਾ ਹੈ ਤਾਂ ਇਸ ਵਿੱਚ ਧਰਤੀ ਦੇ gravitational force ਦੇ opposite ਇਸ ਦੀ position ਦੇ ਕਾਰਨ ਇਸ ਵਿੱਚ potential energy ਅਤੇ ਇਸ ਦੇ orbital motion ਦੇ ਕਾਰਨ ਇਸ ਵਿੱਚ kinetic energy ਹੁੰਦੀ ਹੈ। The potential energy of the satellite in the orbit at a height h above the surface of Earth is given by U, which is equal to minus g into me into m upon Re plus h. Since the satellite having mass m revolves in its orbit around the planet with an orbital velocity v under the effect of its gravity, therefore, the kinetic energy k of the satellite in its orbit is half of m into v square, which is equal to half of m into g into me upon Re plus h. The kinetic energy is positive, whereas the potential energy is negative. However, in magnitude, the kinetic energy is half of the potential energy. Since the total energy of a satellite in its orbit, E, is the sum of the kinetic energy and potential energy. Therefore, the total energy E is equal to half of m into g into me upon Re plus h minus g into me into m upon Re plus h. That is further equal to minus half of g into me into m upon Re plus h. However, in terms of acceleration due to gravity, total energy E can be obtained by substituting g, me equal to small g, Re square, and we get E is equal to minus half of small g into Re square into m upon Re plus h. It is important to point out that the total energy of a circularly orbiting satellite is negative, with the potential energy being negative but twice as magnitude of the positive kinetic energy. When the orbit of a satellite becomes elliptic, both the kinetic energy and potential energy vary from point to point, but total energy remains a constant, which is negative as in case of a circular orbit. This is what we expect, because if the total energy is positive or zero, the object escapes to infinity. Satellites are always at finite distance from the Earth, and hence their energies cannot be positive or zero. For this reason, the planet and the orbiting satellite are said to form a bound system. In order to free the satellite from the gravitational field of the planet, an energy equal to minus E has to be supplied to the satellite. Thus, the binding energy of the satellite is equal to half of g into me into m upon Re plus h.
In general, if the height h of the orbit of the satellite increases, then its kinetic energy will decrease. Its orbital velocity will also decrease, but its potential energy and its total energy will increase as both become more negative.
ਆਮ ਤੌਰ ਤੇ ਜੇ ਸੈਟੇਲਾਈਟ ਤੇ orbit ਦੀ ਹਾਈਟ h ਵੱਧ ਜਾਵੇ ਤਾਂ ਇਸ ਦੀ ਕਾਈਨੈਟਿਕ એનર્ਜੀ ਘਟ ਜਾਵੇਗੀ, orbital velocity ਵੀ ਘਟ ਜਾਵੇਗੀ, ਪਰ potential energy ਅਤੇ total energy ਵੱਧ ਜਾਵੇਗੀ ਕਿਉਂਕਿ ਇਹ ਦੋਵੇਂ ਜ਼ਿਆਦਾ ਨੈਗੇਟਿਵ ਹੋ ਜਾਣਗੀਆਂ। ਅਸੀਂ ਜਾਣਦੇ ਹਾਂ ਕਿ ਅਰਥ ਦੇ ਸੈਟੇਲਾਈਟਸ ਅਰਥ ਦੁਆਲੇ ਘੁੰਮਦੇ ਹਨ। ਮੂਨ ਅਰਥ ਦਾ ਨੈਚੁਰਲ ਸੈਟੇਲਾਈਟ ਹੈ ਜੋ ਲਗਭਗ 27.3 ਦਿਨਾਂ ਦੇ ਸਮੇਂ ਵਿੱਚ ਸਰਕੂਲਰ ਆਰਬਿਟ ਤੇ ਚੱਕਰ ਪੂਰਾ ਕਰਦਾ ਹੈ। The satellites are made for specific tasks. One of the most significant applications of artificial satellites is its use in telecast. Earlier, it was difficult to relay telecast all around the world due to the spherical shape of the Earth. But in last 50 years, there are remarkable changes in communication technology. The backbone of this communication wonder is the variety of satellite systems orbiting around the Earth. The first artificial satellite, Sputnik 1, was launched by USSR on October 4, 1957. Sputnik 1 helped to identify the density of the ionosphere, as well as it also provided the first opportunity for meteoroid detection. Then, Sputnik 2 was launched on November 3, 1957 and carried the first living passenger into orbit. Do you know who was the first living passenger into space? It was a dog named Laika. Explorer 1 was the first American satellite which was launched on January 31, 1958. Satellite systems are classified for different aspects of satellite motion. From the point of physics, orbital classification of satellite systems is more interesting. A geocentric orbit is an orbit around the Earth as that of Moon. This is the orbit of artificial satellite which is launched to revolve around the Earth. Geocentric orbit is further classified on the basis of distance from the Earth's surface. A geostationary orbit. Satellite in this orbit has time period equal to that of the Earth, but the plane of rotation is equatorial plane. Thus, motion of satellite is completely synchronized with the motion of the Earth. Geostationary satellites are used for communication around the world. They cover ground locations, which are close to equator. Polar orbit. The orbit has an inclination of 90 degrees with respect to the equatorial plane and as such passes over the Earth's poles. Polar satellites are important for weather forecasting. ਅਸੀਂ geostationary orbit ਦਾ ਜ਼ਿਕਰ ਕੀਤਾ ਹੈ ਜਿੱਥੇ ਸੈਟੇਲਾਈਟ ਦਾ ਟਾਈਮ ਪੀਰੀਅਡ 24 ਘੰਟੇ ਹੁੰਦਾ ਹੈ ਪਰ ਜੇ ਸੈਟੇਲਾਈਟ ਦੇ ਚੱਕਰ ਦੇ 24 ਘੰਟੇ ਜੋ ਅਰਥ ਤੇ ਆਪਣੇ ਐਕਸਿਸ ਤੇ 24 ਘੰਟੇ ਵਿੱਚ ਘੁੰਮਣ ਦੇ ਬਰਾਬਰ ਹੈ ਤਾਂ ਇਸ ਤਰ੍ਹਾਂ ਛੱਡਿਆ ਗਿਆ ਸੈਟੇਲਾਈਟ ਅਰਥ ਤੇ ਉਸੇ ਸਥਾਨ ਤੇ ਰਹੇਗਾ ਅਤੇ ਇਹ ਸਟੇਸ਼ਨਰੀ ਦਿਸੇਗਾ। ਅਸੀਂ ਜਾਣਦੇ ਹਾਂ ਕਿ ਅਰਥ ਤੇ ਸੈਟੇਲਾਈਟ ਦਾ ਪੀਰੀਅਡ ਆਫ ਰੈਵੋਲੂਸ਼ਨ ਇਸ ਦੀ ਅਰਥ ਤੇ ਸਰਫੇਸ ਤੋਂ ਹਾਈਟ ਤੇ ਨਿਰਭਰ ਕਰਦਾ ਹੈ। ਆਓ ਉਸ ਸੈਟੇਲਾਈਟ ਦੀ ਹਾਈਟ ਦੀ ਗਣਨਾ ਕਰੀਏ ਜੋ ਅਰਥ ਤੇ ਸਰਫੇਸ ਤੋਂ ਉੱਪਰ 24 ਘੰਟੇ ਵਿੱਚ ਇੱਕ ਪਰਿਕਰਮਾ ਪੂਰੀ ਕਰਦਾ ਹੈ। Since period of revolution of Earth T is equal to 24 hours, that is 24 into 3600 seconds, radius of Earth RE is equal to 6.4 into 10 to the power 6 meter and acceleration due to gravity at the Earth's surface is 9.81 meter per second square. On substituting these values in the expression for h, which is equal to cube root of small g into re square, t square upon 4 pi square minus re, the height of the satellite would be cube root of 9.81 into square of 6.4 into 10 to the power 6 into square of 24 into 3600 upon 4 into square of 3.14 minus 6.4 into 10 to the power 6. This gives h equal to 42,343 kilometers minus 6,400 kilometer. That is 35,943 kilometers. Thus, a satellite will appear stationary if it revolves around the Earth from west to east in an orbit coplanar with the equatorial plane at a height of about 36,000 kilometers above the surface of Earth. Such an orbit is also known as parking orbit, and the satellite revolving in this orbit is called a geostationary satellite or simply a stationary satellite. However, the orbital velocity in a geostationary satellite comes out to be about 3.08 kilometers per second. Since 1957, advances in technology have enabled many countries, including India, to launch artificial Earth satellites for practical use in fields like telecommunication, geophysics, and meteorology. On April 19, 1975, India entered the space age with the launching of the low-orbit satellite Aryabhatta. In the first few years of its program, the launch vehicles were provided by the former Soviet Union. However, on August 10, 1979, our self-made launch vehicles were employed and sent the Rohini series of satellites into space. In India, program to send polar satellites into space began in late 1980s. A series of satellites labeled IRS, that is, Indian Remote Sensing Satellites, have been launched. The INSAT or Indian National Satellite series of satellites were designed and made operational for communications and weather prediction purposes beginning in 1982. India tested its geostationary satellite capability in 2001 when it sent an experimental communications satellite GSAT-1 into space. I hope you are well versed with the concept of gravitation. Let us now summarize today's topic. Velocity, which is required to put the satellite into its orbit around the Earth, is known as orbital velocity of the satellite. If a satellite of mass m moving in an orbit around the Earth at a height h above its surface, then its orbital velocity v is equal to square root of g into me upon re plus h. However, orbital velocity in terms of acceleration due to gravity would be v equal to re into square root of small g upon re plus h. It is important that the orbital velocity of a satellite is independent of the mass of the satellite. However, the time taken by the satellite to go once around the Earth is known as its time period of rotation, which can be measured as t equal to 2 pi into square root of cube of re plus h upon g me. In terms of acceleration due to gravity, it would be 2 pi upon re into square root of re plus h whole cube upon small g. Using this expression for time period, one can measure the height of the satellite, according to which h is equal to cube root of small g into re square t square upon 4 pi square minus re. When a satellite revolves around a planet in its orbit, it possesses both potential energy and kinetic energy. The potential energy of the satellite U is equal to minus g into me into m upon re plus h, and the kinetic energy of the satellite K is equal to half of m into g into me upon re plus h. Therefore, the total energy of a satellite in its orbit E is equal to minus half of g into me into m upon re plus h. Total energy of a circularly orbiting satellite is negative. Since the satellites are always at finite distances from the Earth, therefore their energies cannot be positive or zero. Some important types of satellites are classified as geocentric orbit. This is the orbit of artificial satellite, which revolves around the Earth. Geostationary orbit. Satellite in this orbit has time period equal to 24 hours and the plane of rotation is equatorial plane. Polar orbit. The orbit has an inclination of 90 degree with respect to the equatorial plane and passes over the Earth's poles. So now we come to the end of today's topic. Here's a quick test for you to find out how much you have actually learned. My first question is, define a geostationary satellite. The answer to this is satellite that has time period equal to that of the Earth and the plane of rotation is equatorial plane is called a geostationary satellite. The next question, what is the height of a geostationary satellite from the Earth's surface? Yes, it is about 35,943 kilometers. The next question, define orbital velocity. Its answer is, orbital velocity is the velocity which is required to put the satellite into its orbit around the Earth. Next question, give the expression for orbital velocity at the surface of the Earth. The answer is, at the surface of the Earth, orbital velocity V0 is equal to the square root of small g into Re. The next question goes like this, what is the total energy of an orbit? Its answer is, total energy of a satellite in its orbit E is equal to minus half of g into me into m upon Re plus h. And the last question, what is the significance of negative sign in this expression? Answer, if the total energy is positive or zero, the object escapes to infinity. I am confident that you have all understood the topic very well. I hope you enjoyed the lesson as much as I did and are looking forward to the next class. Thank you for your attention and see you next time again.